Okay, so please settle down. Okay, so please settle down, then we can get started. Okay, so last lecture we finished on some basic C programming. Okay, so we are slightly behind the planned schedule. Okay, but that is fine. Tomorrow is also a holiday. Okay, so you're going to miss 1 hour of tomorrow. Correct? Okay, but not to worry. So we will progress, and along the way we will make some adjustments towards the end. Okay, depending on where we are. Okay, so we will still carry on. Okay, and then we will fine tune maybe the last part. Okay, depending on what I can sort of cut short if we don't have time. Okay, so we still have a few more topics on basic C programming concept before we start the news processor. Okay, so this topic here, lecture 3 on data representation number systems, is quite important. Why? Because this will actually play a very significant role in the rest of your module here. Okay, even though C programming is only the first part, this representation and number system, you will see it again and again in all the remaining topics. Okay, MIPS processor, your Boolean logic, your digital gates, and so on. Okay, so this is important that you understand how this thing works. Okay, so we're going to talk about number systems and representation. Okay, so let's just go straight into it. Okay, ASCII code, negative numbers. Okay, how we represent negative numbers in a binary system, and also how we represent real numbers. Real numbers as in decimal point numbers. Correct? How do we represent them within the binary scope? Okay, so when you write a C program, your type is important. So in other languages, okay, you may just declare a variable as var and you can just put anything inside. Okay, whereas in C is very strongly typed. Okay, so you need to specify what is the data type that this variable is going to hold, and you need to sort of stick to it. Okay. How data is represented depends on its type. Okay, always remember your computer system is recognizing only ones and zeros. Okay, ultimately it's all ones and zeros. How we interpret the data is only the human who does it. Okay, so when you have ones and zeros, when we interpret it, depend on what we look at it as. Is this ones and zeros bit stream representing a character? Is it an integer? Is it a positive number? Is it a negative number? Only we know. Correct? So we must be able to interpret it correctly. Okay? Take for example these two bit streams. What do they represent? If I just throw this ones and zeros to you, you cannot interpret. Okay? Unless I tell you that this is representing, for example, a 2's complement number, then you know how to decode it. Or if I tell you that this is a floating point number, then you know how to decode. Okay, without any idea of what it represents, you have no idea how to decode it. Okay, so if I say that this 8-bit number is an integer, then you will decode it to be, say, it represents 70. Okay, how it represents 70, you will see in a while. Okay, if I say this is a character, then you say this represents character F. Okay, not the ideal letter to look forward to, but in this case, it represents letter F. Okay, the string below, what does it represent? If I say that this is an integer, then you get this very, very small integer number. Okay, but at the same time, if I say that this is a float, then it represents minus 6.5. Okay, so it's just the same ones and zeros, but if I tell you that this is actually representing this format, then the way I interpret this 1 and 0 becomes totally different. Okay, so that is the important takeaway from this set of lecture material that we're going to go through. Okay, so eventually your binary bits are nothing more than ones and zeros. In most basic units, we will refer to bytes, which is 8 bits. Okay, nibble is rarely used, 4 bits. Okay, word is open to interpretation. What is exactly one word? There is no clear definition. Okay, in some cases, one word can be 2 bytes. In some system can be 4 bytes. In some system can be 8 bytes. Okay, so the representation of what exactly is word is open. It's not specific. How many bits can represent how many values? So if I have n bits, I represent 2 to the power n values. Correct? That part we should know. So if I have 2 bits, okay, so if 2 bits means 2 to the power of 2. Okay, that means you got 0, 0, 0, 1, 1, 0, and 1, 1. Correct? And so on. So 4 bits, 2 to the power of 4. So those are all the representations that I can get depending on how many bits I have. Okay, so if you say that your system, your computer system is 32 bits, then I can represent up to 2 to the power of 32 different numbers, correct, within that system. To represent m values, you need log to the base 2m ceiling function to know how many bits are required. Okay, this one you'll see more example later. Okay, so for example, if I want to represent 1000 values, okay, so if I plug in the formula, I will see that I require 10 bits. Why? Because 1000 does not equate to any 2 to the power or something. Correct? So I need to take the ceiling. That means I need to have more bits than I actually need. Okay, if my number is not a specific 2 power number. Okay, so all our life we have been dealing and been counting from what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we go on to 11 and so on. Okay, so from the time we were 1 or 2 years old, we started counting this way and we carry on counting this way. Okay, but we never questioned why must we count this way, alright? Okay, and the reason is because this numbering system is called the base 10 numbering system. Okay, all our life we've been using it, but maybe we never realize it. Okay, so all our life we've actually been using the base 10 number system. So if I say I have a number called 1, 2, 3, how do I say this is 123? Okay, so each of it has a base 10 to it, and the first index is index 0, so it's 10 to the power 0 multiplied by 3. The next index is index 1, so this is 10 to the power 1 multiplied by 2. And the next index is 2, so this is 10 to the power of 2 multiplied by 1. Correct? Then I add up all this together, I will get 123. Okay, so when we count normally, we say that we are actually using the base 10 number system. Okay, except that nobody will, okay, we are so used to the number system that if I give you a number called 775, we will not think so much. 10 to the power 0 times 5, 10 to the power 1, we won't do that. Alright, because we have grown up in this number system. So when I look at 775, I straight away know that it's 775. Okay, so there is no confusion about it because we have grown up to that. And from the decimal point onwards, the power is the same except that it is, instead of 0, 1, 2, 3, it goes in the opposite direction of -1, -2 and so on. So that is how you get your decimal values here. Okay, so for a base 10 number system, we straight away know what it represents and how to interpret it. Okay, so when we say base 10, what does it mean? There's a total of 10 different symbols in this base. Okay, the 10 different symbols are what? 0 to 9. Alright, so after 9, of course, you overlap back to 0 and so on. That's how we count. Okay, so for a base 10, we have a total of 10 different symbols in the system. Okay, so this is of course the mathematical representation of how we interpret the number. So A is your all your positive numbers, all your integer numbers, and F is all your decimal point numbers. So in binary, in computer systems, there are other base systems that we deal with. And the most common one is of course your binary system, which is your base 2. Okay, why base 2? Because only 2 symbols, 0 and 1. Okay, ultimately it comes down to zeros and ones. Okay, ultimately it's only 0 and 1. Okay, but in order to make our life easier, correct, in terms of looking at zeros and ones and trying to interpret it more easily, we will actually use this hexadecimal system more. Okay, so hexadecimal system is also very, very popular in computing language. Why? Because you can represent your binary bits in a more compact fashion. Okay, and it's much more easier to read and understand. Okay, and in hexadecimal, use base 16. Okay, base 16 means total of 16 different symbols. And what are the symbols? 0 all the way to 9, which is your base 10, followed by A to F. Okay, so total of 16 different symbols. That means what? That means when I count from 0 all the way to 9, the next digit after 9 is A, B, C, D, E, F. Only after I reach F, then I roll over back to 0. Okay, so that is what is a base 16 system. There is of course another system here called base 8, which is also occasionally used, but very rarely do you see it in most cases. Okay, but it's also there. Okay, so sometimes, in some instances, we may choose to represent a number in base 8. Okay, so from this you can see that actually you can come up with any form of number system. Okay, and you can generalize it to say it is base R. Correct? Why? Because depending on how many symbols I want, I just say this is the new base. Correct? So if I want a base 6 system, so I say count from 0 to 5. Then from 5 onwards, I roll over. Okay? So ultimately, you can actually come up with any base R system that you like. Okay? In computing, the most common is of course your binary and your hexadecimal. Okay? And these are the two base main systems you will see again and again. Okay? In all your material. How do you represent numbers? Okay? When you're writing your code, okay, different languages have different formats, okay, in representing numbers. When I declare a variable, okay, integer num, okay, and I say this is equals to 55. By default, if I just put a number, it is base 10, correct? That is how we always interpret it. Without any other changes or anything addition, we always say this is a base 10. So when I see 55, automatically I say that this is a base 10 system, 55. Okay, but again, if I put 55 and I put a 0x in front, then it becomes what? Okay, or a 0h in front in some cases, then it becomes a hexadecimal number, which is totally different. 0x55 and just 55 are totally two different numbers. Okay, how to interpret 0x55, we will look at that in a while. Okay, so again, you must always remember, when I don't put anything, by default we say a decimal. But if I want to represent this as a binary number or a hexadecimal number, then I must put some notation in front, okay, or some prefix in front. In C programming, for hexadecimal, we will say we put 0x. Okay. In most programming languages, hexadecimal is represented either by 0x or 0h, or in some case 8h, depending on what is the programming language you're using. Okay, for binary, you can usually use 0b, okay, which is what we will use in our Qt Spim later, your MIPS assembly language. Okay, so in different languages, you need to add different kind of prefix before the number to say that this represents either a binary number or a hexadecimal number. Okay, so how do I do the conversion? Depending on the base, is the same thing. Okay, so what I did just now earlier for the base 10. Okay, so what did we do earlier for the base 10? If I say that this is a base 10 number, okay, whatever is the number from the decimal point going backwards, it is index 0, index 1, index 2, index 3, and so on, correct? Okay, and if I say that this is base 10, it's 10 to the power of 0 multiplied by whatever number is here. Then followed by 10 to the power of 1 multiplied by whatever number is here. Okay, then if I have a decimal point, after that it will become minus 1, minus 2, minus 3. So this is 10 to the power of minus 1 multiplied by whatever number is here. Okay, then I just add up everything, I get my final value. The same thing applies to all your bases. The only difference is what is the base. What is the base? So only the base changes. So if I say that right now I'm going to use a base 2 system, it is exactly the same process. So in this case, this is before the decimal. So I say that this is interpreted as what? 1101 is represented as, this is 2 to the power of 0 multiplied by 1. Correct? And then this is 2 to the power of 1 multiplied by 0. Okay, this is 2 to the power of 2 multiplied by 1, and this is 2 to the power of 3 multiplied by 1. Then I add up all of that together, that gives me the front part. Okay, then I have a decimal place here, 101. Okay, so that 101, how do I interpret, is 2 to the power of minus 1 multiplied by 1, 2 to the power of minus 2 multiplied by 0, and 2 to the power of minus 3 multiplied by 1. Alright, and I add up all of that, that will give me the decimal part. Okay, so I add these two together and I get the final answer. Okay, so of course in binary, since anything multiplied by 0 is always 0, we don't waste time with that. So we only focus on those that have a 1 in it. So whatever there's a 0, we can straight away ignore. Okay, because it has no impact. Okay, so that is how you get your final answer. So regardless of the base, the process is still the same. Okay, so now if I say that this is a base 8, it's still the same process. Okay, only thing the base has changed, but the same process follows through. Okay, and I get my final answer. Okay, so of course when you deal with hexadecimal number, you must remember what the hexadecimal digits represent. What does A represent? A is after 9, correct? So A is 10. B is 11, 12, 13, 14, 15. So A to F is 10 to 15. Okay, so that's the only thing you must take note of. When you're dealing with hexadecimal or base 16, A to F is represented by 10 to 15. Okay, so again, base 5. Base 5 is something we have not seen before, but if you suddenly are given a question in base 5, the same process holds true. Okay, how do I do conversion? What is the easiest way to do conversion for any form of numbers? What's the easiest way? Calculator. Our exam all got calculator, so don't need to worry one. Okay? Except what? Except if the question says show me the working. Don't say I use my calculator, so no working. Okay? That's not an acceptable answer. Okay? So of course, if you don't have a calculator, how do you do it? Okay? So there is 2 steps to it. But calculator, the problem is what? Calculator, most calculators only deal with the whole number part. Okay, very rarely you can find calculator that can give you the decimal or the fractional part, okay, in conversion. Okay, so that is the thing that you still need to do anyway by hand. So for example, 43, how do I convert to or get my equivalent binary number? Okay, so the step is very simple. I continuously divide by 2. Okay, until I hit 0. So when I divide by 2, I get 21, and I get a remainder 1. Correct? So the very first remainder that I get, that will be my least significant bit. Okay, so that is my least significant bit. Then I again divide by 2, I get 10. Okay, I still get a remainder 1. So that is my next bit, and so on. Okay, so I build up from there until I divide and I get 0. Okay, so I continuously do that, I get my final answer. Okay, so 10, 10, 11. How about the decimal part? The decimal part, I must do multiplication continuously by 2. Okay, so if I have 0.3125, how do I know what is the equivalent binary representation? Okay, so I multiply by 2, and each time I look at what is the value in front of the decimal. Okay, and that value will form the binary portion for me. So the difference is what? In the whole number part, the very first number is your LSB. But in my fractional part, the very first digit is your MSB. Okay, so that part you must be careful. If not, you get everything the other way around. Okay, so you continuously do until you get your final answer as 1. Once you hit 1, that means you can stop. Okay, so that is how you do your multiplication by 2. Okay, so conversion between decimal and other bases. Okay, so we saw decimal to binary, okay, for whole number part and fractional part. Okay, once you convert to decimal, you can of course easily reconvert back to other bases as well. Okay, so once I get a decimal representation, I can convert to hexadecimal, I can convert to octal, and so on. There is also shortcut, okay, to convert between 2, 4, 8, and 16. Okay, what is the shortcut? The shortcut is basically how you group them together. Okay, so we know that octal means what? Okay, octal means total of 8, correct? And 8 means what? Represented by 3 bits, correct? Okay, octal is represented by 3 bits. So what I need to do is whatever number I have, I group it in 3s. Okay, and each group of 3 is representing one number. Okay, so all I need to do is to say that this 001 is 1, 011 is 3, correct? And 111 is 7, and so on. 10 is 2. So the most significant number, if there is no leading 0, you add a 0 yourself. Correct? If the most significant bit is less than 3, then you add pad zeros in front. Okay? So in octal, you say you group in 3. Okay, if I want to do the reverse, every octal number will then represented by 3 binary bits. Okay, so 1 will go to 001, 3 will go to 011, and so on. Okay, so all this conversion, don't worry, after a while you will know it by heart. So you automatically know what is binary representation of A, what is binary representation of 9, and so on. After a while you get used to it. Hexadecimal is the same thing. Hexadecimal is base 16. Base 16 means what? 4 bits. Base 16 is 4 bit. So everything is in groups of 4. So all I need to do is whatever bit pattern I have, I group it in groups of 4. Okay, so in this case, the most significant bit is only 3 bits, so I pad a 0 in front. So I get this. Okay, when I convert, this is what I'll get. Okay, so you can see that it's actually quite straightforward once you yourself know the representation easily. Okay, so as long as you know 0 to F, what are the binary bit pattern by heart, you know already, means it just becomes very straightforward. Okay, so of course you can always use your calculator to do it. Okay, let me see, where's our calculator here. Okay, so let me just show you. In our calculator, we have programmer mode. Okay, so under programmer mode, you can key in any number and it will show you the equivalent. So for example, if I key in 25 in decimal, it will automatically show me octal representation, hexadecimal representation, and binary representation. Okay, so all your calculators can do this. Even your standalone calculators can do it. Okay, so you can straight away use your calculator to know the answer as well. Okay, so that are the basic representation. Okay, binary, octal, hexadecimal. Now another important code called ASCII Code. Okay, this ASCII Code stands for American Standard Code for Information Exchange. Okay. Okay, so why this ASCII code in the first place? So sometimes you must know the history of why ASCII code. This ASCII code actually came about, okay, when computers started gaining popularity and people started to think how to manufacture keyboard, correct? How to transmit character, okay? So how do I transmit a character? How do I manufacture a keyboard anywhere in the world and say that it's compatible? That means if I press the A here, another keyboard, and I press the A, they must both transmit the same code to my computer, correct? Okay, so there must be a uniform language, a uniform representation on how different characters are represented. So that is why they came out with this standard called ASCII code. Okay, and this ASCII code basically has 7 bits of data plus 1 parity bit. You all know what is parity bit? Have heard before? Okay, parity bit is actually used to do what? Is to do error checking. Okay, so when you say odd or even parity, means what it does is it counts the number of ones inside your data packet. Okay, so for example, okay, so let's assume that my most significant bit is my parity bit. Okay, so I got 8 bit of data, total is 1 parity bit and 7 bit of data here. Okay, and let's assume my data I'm transmitting is 0, 1, 1, 1, 1, 1, 0. Okay, and then I say that I am transmitting this across the channel. Okay, and I put in a 1 here. So what is the total number of ones? 1, 2, 3, 4, 5, 6, correct? Okay, and if I say that this is even parity check, okay, let's say I'm doing even parity check in my system. So if I transmit this data and over the receive side I receive this data, okay, how can the receiver know that what I receive is correct, okay, or some data corrupted along the way? Okay, so if I prearrange that the sender and receiver both are performing even parity check, that means when I receive the data, I would go and count how many ones are there. Okay, if I say I'm following even parity, means I expect an even number of ones. Correct? So I will come and check. Okay, so 1, 0, 1, 1, 1, 1, 1, 0. So 1, 2, 3, 4, 5, 6. So I receive 6 ones. So I assume it's correct. Okay, so that is where the error checking comes in. So if I happen to receive this, okay, then when I count, what do I get? I get odd number of ones, correct? Okay, so I know that something went wrong, correct? That means this data has some error in it. I should not take it, correct? Of course, this is very basic and primitive error checking, correct? Why? Because it does not account for double error, correct? If 2-bit flip, then it still come back to the same problem. If 2-bit flip, then I still come back to the same even number of ones or odd number of ones. Okay, so this is a very primitive form of checking. Okay, but it is still used for all this kind of simple system. Correct? Because keyboard, what's the worst that can happen? You just delete and type again. Correct? Nothing significant. Nothing significant. So it's fine. Okay, so that is where we use this. So this is a representation of the ASCII code. Okay, next page you see the full table. Okay, so this is the full table. So you can see that every character from your keyboard or from your system is actually mapped to a specific bit pattern. Okay, so when you are typing something, you are actually transmitting all these codes over your cable or wirelessly to your system. Okay, so you can see 7 bit. These are the most significant bit and least significant bit. Okay, so for example, if I want to transmit letter G, okay, what are the 7 bits? If I want to transmit letter G, means what? The most significant bit will be 1, 0, 0, correct? This table here. And the least significant bit is this one, correct? 0, 1, 1, 1, correct? Okay, and of course, I need to then decide what is my parity bit. Is it going to be 1 or 0 depending on what is the system configuration? Okay, so that is ASCII table and ASCII code. Okay, when will you use this? You will use this if you are designing a system and you are trying to display characters, correct? And then you need to know how to transmit your characters correctly. Okay, so that is where this kind of table will be useful. Okay, so coming back to our previous slide just now on the bit pattern. So if again I look at this bit pattern, and if I tell you, and I don't tell you anything, you can interpret it any way you like. Correct? So if I say this is an integer, then I say it's 70. How do I know it's 70? Because this is base 2, correct? Binary is base 2. So this is 2 to the power of 1, 2 to the power of 2, 3, 4, 5, 6. 2 to the power of 6. Correct? So you add all these 3 together, you will get 70. 2 power 6 plus 2 power 2 plus 2 power 1. Then you get 70. If I say that this binary bit pattern, this 8-bit pattern is a character, then what will you do? You will look at the ASCII table. So I will say, okay, what are the upper 3 bits? Okay, so if I say this is a character, then I'll look at what are the upper 3 bits and what are the lower 4 bits. Okay, so the upper 3 bit 100 and 0110, correct? So let's look at the table. Okay, so 100 and 0110 is one here. Okay, so the upper bits is this 100 and the lower bits are 0110. That is how I get the F. Okay, so the same 8 bits, okay, if I say this is an integer, you will say it is 70. If now I say that this 8 bits is representing a character, you say it represents character F. Okay, so that is the representation of data. In C, both character and integer somehow can be interchanged. Because it all depends on how I want to display this data. Okay, what do I mean by that? You can see that, for example, here, if num is declared as an integer, and I say it's 65, character is, this ch variable character is declared as a char, that means a character variable. Whenever you want to assign a value to a character variable, if you want to assign a ASCII value to a character variable, you must use the single quote here. If you don't use single quote and you just put an F there or you put an A, whatever, it will show error. It will show a compile error. So what am I trying to do? When I put a single quote and I put this alphabet there, that means I'm trying to assign the ASCII value of this symbol to this variable here. Okay, the ASCII value. So what is the ASCII value of F? Is this binary string here, 0100 0110, and I'm trying to take this and assign it to my variable called ch here. Okay, when I try to print out, what will happen here? Okay, you can see that when I print out num holds a value of 65. Okay, num holds a value of 65. So when you see 65, you say it's an integer. Correct? You say 65 is an integer. But 65, what does it represent in terms of binary? Okay, what does it represent in binary? So let's look at that. Okay, so if I say 65 here, okay, 0100 0001. Okay, so let's come back here. Okay, 0100 0001. So if I split it up here, this is the MSB, this is the LSB. Okay, so if I go back to my table here, 100 and 0001. 100 is here and 0001 is here. So that represents my A, correct? That represents my A here, uppercase A. So when I try to print out, if I use %d, your format specifier, your C program will interpret the data that I sent to it as an integer and print out the integer version. But when I use %c, it's interpreting it as a character. So even though my variable is declared as an integer, okay, but when I use %c to print it out, it will interpret it as if you want to print out the character equivalent. That means the ASCII equivalent. So that is why it prints out A over here. Okay, so this thing you must remember. So even though my variable is declared as int, I can still use %c to print out. Okay, and then it will interpret it as if it is a character variable. Okay, how about the next one here? Okay, the same thing. Even though my character is ch is declared as a character variable, if I use %d, I get the number. But when I use %c, I get the ASCII equivalent. The data did not change, correct? The same binary bit pattern is always there. But depending on whether I use %c or whether I use %d, the interpretation is different. So your C program will interpret it as either you want to display this data as a character or you want to display this data as an integer. But the data is still the same. Nothing has changed. Okay, so that's why I always say the ones and zeros are always ones and zeros. The interpretation is only the human side. Only we know what we're talking about, or we don't know what we're talking about, correct? Either way. Okay, so let's look at this past year question. Okay, so we haven't come to loops yet, but don't worry, we will come to that. So this one is basically a loop, we will come to that shortly, but this loop is supposed to run 10 times, and in the 10 times, I'm increasing this number stored inside the variable n. Okay, so the question is asking if I take this variable and I run this loop 10 times, each time I increment by 1, what will be the output? So is it from 40, I increase until it becomes 50. So this is the answer. Okay, so the answer to this we will see in a later slide. Okay, but don't worry, we will come to that. Okay, now let's look at negative numbers. So far we have only been focusing on positive numbers. Correct, only positive numbers. Okay, so all the while is positive numbers. Now let's look at negative numbers. Because when you declare a variable, you can store positive numbers as well as negative numbers inside. Okay, so if I declare integer, okay, Okay, I can put in a negative number inside as well. Okay, or I can put a positive number inside. How do I represent a negative number? So there are three common representations in our binary number system: sign and magnitude, ones complement and twos complement. Okay, the one that we will see again and again most of the time is the last one, the twos complement. Okay, why twos complement? Because that is the default representation used by all computing systems. Later I'll show you. Your calculator, your computer, everybody uses the twos complement system. Okay, but we also need to know sign, magnitude, and ones complement because those are also used occasionally in some other systems. Okay, sign magnitude is very straightforward. You just use the most significant bit to represent the sign. That means if my most significant bit is 0, then I say I'm representing a positive number. If my most significant bit is 1, then I say it's a negative number. Okay, so it's very easy and straightforward. So from 8 bits that I have, the most significant bit is used for sign, and the remaining 7 bits is used to represent the actual data. Okay, so if I give you this binary bit pattern, you just discard the most significant bit to find the actual value, and then use the sign bit to know whether it's supposed to be a plus or minus. Okay, so if the most significant bit is 0, then it's a plus. If not, it is a negative number. Okay, so that is a very easy and straightforward representation. Okay, so that is the sign and magnitude representation. So what is the range we get? So the largest number you can get is when the most significant bit is 0 and everything is 1. Okay, that will give me plus 127. The other extreme end, the smallest value you can get is the most significant bit is 1, and again everything is 1, I get negative 127. But in this case, you have two representations for 0. Why? Because you can have a plus 0 and minus 0. Correct? Because as long as the remaining 7 bits are all 0, the most significant bit 0 or 1, it still becomes 0. Okay? So the range you get is minus 127 to plus 127. Okay? So what is the range of values that can be represented? Okay, so for 8-bit, what is the highest value? Okay, so let's look at the calculator a bit. So 8-bit number. Let me switch to scientific mode here. Okay, so if I say 2 power 8, what do I get? 256, correct? Okay, so this number here is actually what? 2 power 7, correct? Minus 1. Correct? 2 power 7 minus 1. So this representation here gives me 2 to the power of n minus 1 to 2 to the power of n minus 1 here. Alright? So if my n is my 8-bit, means I'm actually going from 2 to the power of n minus 1 minus all the way to 2 to the power of n minus 1 plus. That is the range of values that I get, okay, for this sign and magnitude representation. So this is minus, still got a minus 1 here. Okay, just to check it. This is 2 to the power of 7 is 128, correct? Okay, so 127 is 2 to the power of n minus 1 minus 1. Okay, so this is the positive range and this is the negative range. So this is the full range that you get for this sign and magnitude system. Okay, so if I give you any number and I ask you to find the negative equivalent, okay, so if I say that find negative 5, for example, all you need to do is what? To find negative 5, you just represent 5. 5 is 101. Okay, and then I pad it with the remaining zeros. Okay, and the most significant bit will now become 1. Okay, if the most significant bit is 0, then it becomes a positive 5. So this is my negative 5, and this is my positive 5. Okay, so for sign and magnitude, you just use the most significant bit to represent the sign and the remaining bits to represent the value. Okay, next is 1's complement. Okay, 1's complement, this is the mathematical representation. Okay, but the easy way to do it is to very simply just invert all the bits. Okay, so the 1's complement is actually the actual representation with all the bits inverted. That's why we call it the 1's complement. Okay, so for example, if I say 12 is represented by this, okay, so 12 is given by this 0, 0, 0, 0, 1, 1, 0, 0. Okay, this is 12. And I tell you, show me what is negative 12 in terms of 1's complement. All you need to do is to just invert all the bits 1, 1, 1, 1, 0, 0, 1, 1. That's all. Okay, so the mathematical way of doing it is to take to the power n minus x minus 1. You still get the same answer. Okay, whether you use the math to do it or you just invert all the bits. Okay, so in terms of the range, it is the same as just now. Okay, minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So this sign, magnitude range and 1's complement range is the same. Why? Because your plus 0 and minus 0, there are two representations. Okay, so this is the range that you get for the 1's complement. And you can see that for the 1's complement representation, the most significant bit, it is still, in a sense, representing whether it's plus or minus. So when I say that this is a 1's complement number, when I look at the most significant bit, I will automatically know whether this is a positive number or negative number based on just looking at that most significant bit. Okay, if it's a 0, it's positive. If it's a 1, it's negative. Okay, so that is your 1's complement. So for example, 80. How do I find the 1's complement of 80? Okay, so all you need to do is look at what is 80 in your calculator. Okay, so in programmer, you key in 80. Okay, you get your binary representation here. 0, 1, 0, 1, 0, 0, 0, 0, correct? Okay, so here I will get 0, 1, 0, 1. Okay, so the 1's complement is basically I invert all the bits, which means we get 1, 0, 1, 0, 1, 1, 1, 1. Okay, so that is negative 80. Okay, if you use your calculator later, you will see you will not get this. You will get the 2's complement, which is what we are going to do now. Okay, so that's why I never show you the calculator. So sign, magnitude, and 1's complement you still need to do manually. Okay, the 2's complement is the only thing that will happen automatically for you in the calculator. Okay, so let's look at 2's complement, which is the most preferred system. So in 2's complement this is the mathematical representation. Okay, and how do I do it in terms of binary? All I need to do is invert all the bits as before, then plus one more step, add 1. Okay, you invert all the bits, then you have one more step, which is to add 1. Okay, so let me show you. So just now we did this. Okay, minus 80. Okay, so if I give you 80, this is 80 here. Okay, so this is 80. If I say 1's complement, you invert. So if I invert everything, I get the 1's complement. Okay, if I say now give me the 2's complement, all you need to do is add 1. Okay, 2's complement is the 1's complement, add 1. So now very simple mathematics. 1 plus 1 is what? Those say 2 means I ask you for Kahoot quiz. 1 plus 1 is 0. 0 then what? Carry 1. Okay, so in your binary arithmetic, you must remember a few things. 0 plus 0 is what? 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. Okay? So 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 0, carry 1. 0, carry 1. The 1 plus 0 is 1. Then this 1 is 1, 0, 1. Okay? So see this number 1, 0, 1, 1, 0, 0, 0, 0. Okay? So let me show you in the calculator. Okay, so this is 80 if I go and negate it. Okay, don't worry about all the leading ones here. Look at this 1, 0, 1, 1, 0, 0, 0, 0. Alright? So you can see that negative 80 is 1, 0, 1, 1, 0, 0, 0, 0 is what you get here. Okay, so your calculator shows you this by default. The reason why you have all the ones in front is because it will automatically pad the bits depending on how many bit system you have. So if you say 8-bit system, of course it capped at 8-bit. Okay, if the computer is 64-bit, then it will pad once until you fulfill the 64-bit. Okay, so that's why you have all the leading ones in front. Okay, but the actual representation is this. So you can flip back. So this is actual 80. Okay, when I negate it, negative 80 is represented by 10110000. Okay, and how do I get that? I get it by taking the ones complement, which is invert all the bit, then I add 1, then become 2's complement. Okay, so that is how you move from 1's complement to 2's complement here. Okay, so the same number, we can represent it in different pattern, okay, depending on whether you want to say is sign magnitude, 1's complement or 2's complement. Okay, so that is what we are trying to show you here. So again, come back to what we said earlier. Ones and zeros is still ones and zeros. How I interpret is up to us. So we must know whether this 1 and 0, is it a positive number, is it negative number, is it 1's complement, is it 2's complement. Then only we know how to interpret the number. Okay, so let's look at a comparison here. Okay, so you can see that for, let me go back here. Okay, so one of the important thing why we use 2's complement is because in 2's complement, your range is actually minus 128 to 127. Why you get additional one more number is because your 0 is only represented by one representation. In both sign magnitude and 1's complement, you have two versions of 0, plus 0 and minus 0. Okay, which is a waste, correct? It's a waste of a bit stream. Whereas in 2's complement, you only have a single 0 representation. So that is why you have one additional negative number, negative 128 to plus 127. Okay, but again, as before, the 0 and 1 in the most significant bit still represent positive and negative number. Okay, so the moment you know that you are dealing with representation that can be positive or negative, I straight away look at the sign or most significant bit. I will immediately know that it's a positive number or negative number. Okay? Okay, so if I look at this comparison, what is the key difference? The key difference is for my only in sign and magnitude and 1's complement, you have this thing called a negative 0. Okay, whereas in 2's complement, you only have a single positive 0. So since you save up that one allocation, you use it for this one more additional negative number. Okay, negative 8. Okay, so if I take a 4-bit system like this, okay, instead of negative 7 to positive 7 for your 1's complement, in 2's complement, I go from negative 8 to positive 7. Okay, one additional negative number. Okay, so now that you sort of understand this, okay, how do I interpret this? So, when you say your answer is 50, you need to understand this concept of your limit. So you understand that now, when you're dealing with positive and negative number, your range is now almost half. Your range is almost half. Okay, why I say almost half? Okay, imagine that a 4-bit system. For a 4-bit system, that means I have 2 to the power of 4, which means 16 different values. Correct? So rightfully, if I say that all my numbers are positive, that means I should be able to go from 0 all the way to 15. Okay? So if you just think in terms of positive number, what does that mean? From 0, 0, 0, 0, I go all the way to 0, 1, 1, 1. Okay, so 0, 7. And then when I go to the next number, 1, 0, 0, 0, it's actually supposed to be 8, rightfully, if I just carry on counting as if all is positive. But now that my range is split, correct? You have to remember, because the most significant bit is now representing plus or minus. That means my whole range of numbers is effectively split in half. So I cannot go from 0 all the way to 1, 1, 1, 1, 1 and say it's all positive. Halfway through, I will flip over to become negative. So when my most significant number switches from 0 to 1, I'm actually switching over to the negative side of my numbers. Correct? So after 7, what do I get? Okay, after I go to 7 and become 1, 0, 0, 0, okay, I'm actually at negative 8. If I'm using 2's complement number. Okay? And then 1, 0, 0, 1 will become negative 9. Okay? But if I only want to deal with positive number, okay, let's assume that you want your variable to only hold positive number, I do not want to have any negative number, then you can carry on counting from 0 all the way to 15. For that, what must you do? You must declare your variable differently. You cannot just use int. Okay? If I just use int by default, okay, it is considered a signed variable. A signed variable means half positive, half negative. If I only want to stick with all positive number, I must declare it as a unsigned variable. Okay, if I declare my variable as unsigned, then I am going to utilize only the positive range. That means I'll only interpret only positive numbers. So there's no negative. So when a most significant bit flips over from 0 to 1, it will still be considered as 8, 9, 10, and so on. Okay, if I were to declare it as unsigned. But if I don't put anything, then it will automatically be treated as a signed variable. That means half positive, half negative. Okay, so when my most significant bit flip over, I am now switching over to the negative side of my number. Okay, so what is happening here is in your Sunfire system, okay, your integer is 4 bytes, okay, 32 bits. Okay, that means the largest positive integer I can have is 2 to the power of n minus 1 minus 1. That is the largest positive number I can get. So once I hit this positive number, okay, what happened? The next number will be my most significant bit becoming 1. Most significant bit becoming 1. So until this number here, you can see that my most significant bit is 0 and all the remaining bits are 1. So this is the largest positive number I can get in my system. The moment I add 1 to this, then the 1 carry, then the most significant bit flip to become 0 to 1, which means I am now at my smallest negative number. So when this happens, I am switching all the way to negative this, okay, which is negative 2 to the power of n minus 1. Okay, so when I count, I'm going to be now from the smallest negative number all the way counting up, back towards 0. Okay, so at the 10th iteration, this is the number I'll get. Okay, so this is important, okay, when you are dealing with numbers which can grow very large. Okay, and if you do not account for this overflow condition, when the thing wraps around, then you will see that you went up to a very high number, and then instead of carrying on, you went back to the other side. Okay? Okay, the idea of complement can also be extended to a fraction. It's the same thing. So whether I use 1's complement or 2's complement, it's the same thing. So you can see that here, all I do for the fractional part is the same. If it's 1's complement, I flip. If it's 2's complement, I flip, then add 1. Okay, that means I do the ones complement and then add 1. Okay, so that is the same. Okay, so let's take a short break here. Come back in about 10 minutes time. Okay, 5, 10, come back and carry on. the most significant bit become 1. That means all that is now representing a negative number. So you must be able to know that this is a negative number. How do I find the representation of this? I will explain again. Okay, so just now over here I made a mistake. So from minus 8, what should be the next number? Minus 7. Okay, so this is minus 7, minus 6, and so on, not minus 9 just now. Okay, so some of you asked me why is it from 0, 1, 1, it become 1, 0, 0. How do I know that this represents minus 8? Okay, so let's look at how to interpret and get back the equivalent. Okay, so let's assume that I give you this number here, 1, 0, 1, 1, 0, 0, 1, 1. Okay, let's a random number here. Now, when I look at this number, okay, so just now also somebody asked me, just now we talk about the ASCII, correct? And then we say that the most significant bit is parity. So does that mean parity and sign is the same? Is it the same? Okay? Again, come back to the fundamental thing as always. Ones and zeros, the interpretation only we know. That means if I look at this and I say that this 8-bit number is an ASCII number, what must you do? You go look at ASCII table. Correct? You look at ASCII table, go and relate the most significant bit, least significant bit, and find out what is the character it represents. Correct? If now I tell you that this is a 2's complement number, okay, how do I find out the equivalent representation in terms of the decimal? Okay, so for a 2's complement number, if I say that this is a 2's complement number, what is the first thing that you will realize when you look at this? It is a negative number, correct? Because the most significant bit is 1. Okay, so this most significant bit here is a 1, represents a negative. How do I find this equivalent decimal value? What is this decimal equivalent? Is it minus 20? Is it minus 18? How do I do it? So the first step is you must reverse back the process. How did I get 2's complement? I invert and plus 1, correct? So I redo the whole process. So first thing is I invert back. So I do a complement. I say 0, 1, 0, 0, 1, 1, 0, 0. So I take the original number, which is 2's complement, and I first do the 1's complement, correct? And then I add 1 again. So what do I get? 1, 0 plus 1 is 1, 0, 1, 1, 0, 0, 1, 0. Okay, so this is now the bit pattern I get after I do the 1's complement and add 1, correct? Okay, so now what does this represent? Okay, so let's look back at our calculator here. So in binary, I get 0, 1, 0, 0, 1, 1, 0, 1. Okay, and what do I get? I get 77, correct? 77. So what does that mean? That means this number here is 77, and since my most significant bit was a 1, this is negative 77. Okay, so if I were to key in this number in my calculator, what should I get? I should see that it actually represents negative 77, correct? Okay, so if negative is 77, I negate it. What do I get? 1, 0, 1, 1, 0, 0, 1, 1. Can you see? Okay, that is how you take a number that is 2's complement and find the actual equivalent number. You do the 2's complement one more time. Okay, why you do the 2's complement one more time? Because you want to find the equivalent positive side number. But you know it's a negative number, correct? So you find the equivalent positive side number and then you just put a minus sign in front of it. Okay, so that is how you are able to relate. So this number, if I key in my calculator as negative 77, this is the binary representation, which is correct. But without a calculator, how do I know it's negative 77? I must do the 2's complement, find out the actual value, then put a minus sign in front. Okay, so as long as 2's complement is concerned or 1's complement is concerned, you must know that the most significant bit is representing the sign. If it is a positive number, then no need to do anything. Alright? Because a positive number, you don't need to do another 2's complement, it's already a positive sign. Only if it is a negative number, then you do the 2's complement to find the positive equivalent. Okay, and then you put the sign in front. Okay, so that is the only difference here. Okay, so how about addition and subtraction of numbers? Okay, when you are adding numbers, okay, you can have this event known as overflow. Overflow occurs when your result is not within the range of the bits that you have. Okay, when your result is not within the range of the bits that you have. That means if I have a 4-bit system, for example, I know that my range is -8 all the way to +7, correct? Okay, so when I add two numbers together within a 4-bit system, and if my answer is going to be out of this range, then my 4-bit system cannot hold the answer, correct? My 4-bit system cannot hold the answer. So that is when the overflow condition occurs. How do I check for overflow? Okay, if the result does not make sense. When does the result not make sense? When two positive numbers add together and you end up with a negative number. That does not make sense, correct? Okay, or two negative numbers add together and you get a positive number, also does not make sense. Alright, so if the result does not make sense, okay, then you know that the answer has encountered an overflow condition. Okay, how do I do subtraction? Subtraction is nothing more than addition of the complement. Okay, addition of the complement. So if I want to take A subtract B, what I need to do is I need to take the B, 2's complement of it, and then do the addition. Okay, why? Because a minus is nothing more than the addition of the complement of the number. Okay, so that is how you do addition in your system. Okay, so again, overflow is detected when your answer doesn't make sense. Okay, positive to positive become negative, or negative to negative become positive. Okay, so take for example this case here, 5 add with 6. Two positive numbers end up, what do I get? 1011. Okay, so 5 add with 6, what is the answer? The answer is actually what? 11. Alright? Okay, and the answer is 11 is correct. 1011 is correct. Why do I say it's overflow? Because in my mind, I'm saying that these two numbers are sign representation. Okay, always remember, the interpretation is up to the programmer. If I say that these two numbers are unsigned number, a positive number, then the answer is correct, no need to worry, correct? But in my mind, I'm telling that now these two numbers are representing a 4-bit 2's complement representation. Correct? That means I can only have answers within the range of -8 to +7. So 11 is not possible. Okay? So that is the programmer's interpretation. That this number or this arithmetic operation has resulted in an overflow condition. Okay? So you must always remember, you must know what you are dealing with. If you say that this binary representation is signed number, then you must know whether overflow has occurred. If you say this is a unsigned, then is it carry out, for example. Okay, so in cases where there is a carry in the end, okay, so in this case, 1001 add with 1101. Okay, 0 carry 1, 1, 1 plus 1, 0. So there's one more carry out. Okay, you discard the carry. Okay, we discard the carry and we look at the final answer. So again, if I look at this, you can see that two negative numbers add together, I end up with a positive number, so it is an overflow condition. That's how you interpret. Okay, so this discarding the carry is for 2's complement. In 1's complement, you don't discard the carry. In 1's complement, you must still take the carry and add it one more time inside the final result. Now we will see that now. Okay, in 2's complement, you discard the carry and you just look at the most significant bit answer. And then you know whether there's overflow or no overflow. Okay, so these are some of the examples. So you can see very clearly that you just focus on the most significant bit, you will know. Okay, when you just look at the most significant bit, you will automatically know whether an overflow condition has occurred. Okay. So how do I do the subtraction? Like I said before, I convert it to the equivalent 2's complement representation. So negative 7, how do I get negative 7? I know that positive 7 is 0, 1, 1, 1. Correct? Okay, positive 7 is 0, 1, 1, 1. So the 2's complement representation is I invert, then add 1. Correct? Okay, so that is what you get here. Okay, so the 2's complement version is the 1's complement plus 1, that is gives you your negative representation. So I add with the 2's complement version of the number. So that is how you do subtraction. Okay, so you can see here that as long as you get familiarized with the conversion of positive to negative, and you know the difference between 1's and 2's complement, you will get the hang of it. Okay, so in this case, again, what you're doing, 6 minus 1. So minus 1. So 1 is, positive 1 is 0, 0, 0, 1. Correct? So the negative 1 is what? I must do the 1, 1, 1. 1's complement, add with 1. Okay, so that's how you get this. So this represents the 2's complement representation of negative 1. Okay, and after I do the addition, okay, the most significant bit I discard. Okay, so what do I get? So you can see here there is a overflow where? In this condition here. Why? Because positive and negative add together, I get a positive number. Correct? So if the most significant bit, you can see that both of them are negative become positive, or both positive become negative, then it's your overflow condition here. Okay, for 1's complement is almost the same thing, only difference is what? In this step here, you do not discard the carry out. The final carry out, you do not discard it, you must add it back to the result. Okay, that is the only difference. Okay, so in this case, for example, minus 2 and minus 5. So now these are 1's complement representation. Okay, 1's complement representation. So 2 is 0, 0, 1, 0. So minus 2 is just 1, 1, 0, 1. Correct? And 5 is 1, 0, 1. So minus 5 is 1, 0, 1, 0. Okay, that's how you get minus 2 here and minus 5 here. So if I add these two together, finally there is one more carry out here. In 2's complement, addition and subtraction, you discard this carry. Okay, but in 1's complement, you cannot. So this one, you must add it back here. Okay, so that's the only difference. 2's complement and 1's complement, the only difference is in 1's complement, if there's a final carry out after you finish everything, that final carry out has to be brought back and added to the least significant bit one more time. Then you get your final answer. Okay, again, overflow is what? You look at the final answer. Okay, so the final answer is what? In this case, 2 negative number, and your final answer is a positive. Correct? So you know it's an overflow condition. Okay, another form of representation is known as the excess representation. Excess representation is nothing more than just redefining a new 0. Okay, what do I mean by redefining a new 0? Always your 0 is what? All zeros is 0. Okay? But now for example, if I say this is excess 4 representation, okay, when I say excess 4 representation means 4 is now the new 0. So you can see that 4 is now the new 0. So anything after 4, it becomes 1, 2, 3, 4 and so on. Okay, so that is just a new representation. Okay, very rarely we will use all this representation. This is just there. In some specific cases only you might use it. In most cases, it's your normal binary, the hexadecimal, and your 2's complement. These are the most common forms that you must know. Okay, so if I use excess 7 for example, or excess 8 for example, in excess 8 what do I get? Your 8 here becomes your new 0. Okay, so that's the only difference. Okay, so the 0 point has shifted. The numbers are all the same, only thing your 0 point has shifted. Okay, now come to another important section, which is real numbers. Okay, why? Because in most of our cases, we will deal with decimal points. How do I represent decimal points inside my system? Okay, so in fixed point representation, okay, we need to sort of have some part of the bits to say that it represents the integer part, and some part of the bits to say it represents the fractional part. Okay, so for example, in this case, I can say that 8-bit, in this 8 bits, 6-bit I set aside for the whole number, and 2 bits I set aside for the fractional. Then from there, I can say that this is the range of numbers it represents. Okay, so this is one way in which I can sort of decide how binary can be represented in binary in your 2's complement system. Okay, so of course, floating point numbers, when you declare a float, okay, you can have very, very small numbers and very, very large numbers. All right, so you declare a variable as a float, for example, okay, your range is very high. Okay, you can have many, very small numbers. That means you can say 0.0001, or you can have very, very large numbers as well. Okay, how do I represent all of this within that same binary bit stream that I have? Okay, so internationally there is some standard that manufacturers have to follow. Okay, so one of this is called the IEEE 754 floating point representation. Okay, so this is a standard on how we can represent, okay, a binary bit stream to show floating point numbers. Okay, so there is two types. One is called single precision, where you use 32 bits. The other is double precision, 64 bits. Okay, so in our slides, we are only going to look at this single precision format. Okay, so this format is not, it looks confusing, okay, but it's actually quite straightforward as long as you know the mapping of the bits. Okay, so we have 1 bit for sign, which is 0 for positive and 1 for negative. Okay, then mantissa is normalized. Okay, normalized means what? That means whatever is the number, you normalize it until the decimal point is such that you have a single digit and the rest become the fractional part. When you move around the decimal point, what will happen? You will create a multiplication factor here, correct? Now when you move to a decimal point, you create a new multiplication factor with a exponent there. Okay, and this exponent will now play a part over here. Okay, how does it work? Okay, so the first step is whenever you have anything, you normalize it. Normalize it means you just move around the decimal point until you have the first 1, okay, the most significant bit as 1, followed by the rest as fractional part. Okay, and once you move your binary, your decimal point around, you have a new exponent, and now what do you need to do? Okay, so let's look at this example. Once you look at this example, you roughly know the whole idea. How is negative 6.5 represented? Okay, so the first thing we know is it's a negative number, correct? Okay, so once we know it is a negative number, means your most significant sign bit here is going to be a 1. Okay, now the next step is negative 6.5, I represent it as a binary. This one we just saw, correct? 6 is 110 and 0.5 is 0.1, correct, when you convert to your binary representation. So this to this should, when you look back at today's notes, you will know how to do this conversion. Okay, once I do this, the next step is to normalize. Normalize means what? I move my decimal point. Correct? So when I move my decimal point, I get this. So since I move my decimal point 2 places, I must multiply by 2 to the power of 2. in normal base 10, you multiply by 10 to the power of something, correct? That is your normal indices rule. Okay, now here in base 2, so the same indices rule except that now it's base 2, correct? So since I move to the left 2 places, I multiply by 2. Okay, so once I do this step, the rest is just filling the blank only. So what are the blanks you need to fill in? Okay, so I know my sign bit is 1. Now I know that this is 2. The power is raised to 2, to the power 2. So the exponent minus 127 is this new power here 2. So the exponent here is equals to 2 plus 127, which is 129. And 129 is this 8-bit representation. So that is what will come inside here. Okay? And the last part, the mantissa. Mantissa is what? Mantissa is nothing more than the fractional part. So the fractional part is supposed to occupy the remaining number of bits. Okay? So the remaining number of bits are 23 bits here. So the remaining 23 bits will be this fractional part. And since you only have 3 bits, 1, 0, 1, the rest you just pad with all zeros. Okay, the rest you just pad with all zeros. Okay, so again the 3 steps are very easy. The first step is you look at the sign. So if it's a negative sign, you know your most significant bit is a 1. That's the first step. The second step is you convert it to your binary equivalent. Okay. The third step, you shift your decimal place until you normalize it. Normalize means you only have most significant bit as 1 with the decimal point and the rest. And since you shift your decimal point, now you have a multiplication factor which is base 2 to a power. And this power depends on how many decimal points you shift. Correct? Once I know this power, I apply this rule to say the exponent minus 127 is equal to this power. So I know what is the exponent. And the exponent in this case is 129, so the binary equivalent of 129 will come here. And the last part, which is my mantissa, is the fractional part. And then I just pad zeros. Okay, so that is your actual representation in terms of your IEEE 754 floating point. Now, how do I write this as a hexadecimal? Okay, you can see that writing this full 32 bits as a full binary bit pattern is very tedious. So it's much more easier if I can just represent it as hexadecimal format, correct? Okay, so how will I represent it as hexadecimal? I group them in bits of how many? 4, correct? So I start with the most significant. So 1100, 0000, 1101, and the rest are all zeros, correct? Okay, so 1100 is C, this is 0, this is D, and the rest are all zeros. Okay, so that's how you get your full hexadecimal representation of your floating point number. Okay, so again it comes back to the same thing. This is nothing more than 1 and zeros. If I tell you that this binary is a IEEE 754 floating point representation, then you can work backwards to say that this is actually minus 6.5. Correct? If I tell you that this number is a 32-bit sine 2's complement representation, you won't do all this. Correct? You just say that, okay, this is a 32-bit sine number, means this is negative number. I do 2's complement, I find the equivalent number. Correct? Okay? So the 1s and 0s will just be there. You must know what is this representing. Is it representing sine number? Then what do I do? If it's representing IEEE 754 floating point, then what do I do? Okay, if it's representing unsigned number, what do I do? Okay, so you must know the representation so the 1s and 0s can be interpreted correctly. That's all. Okay, so this is what I'm telling you about. Okay, so it's up to you to interpret. Okay, whether it's an integer, is it a negative number, is it a float, or whatever. Okay, so that's the end of this slide. Wait, don't go back first, wait first. Okay, so since tomorrow public holiday, we will end here. But before we go, a few things. Make sure you have registered and you get your slot. Of all the slots, there's only one unearthly slot, which is Tuesday 8 a.m. One tutorial slot at Tuesday 8 a.m. Other than that, everything is earthly timing. Okay? So please stick with your slot. For lab, okay, important. Most of the labs are on time, on target kind of lab, except for the last few. Because the last few is where you need to use the actual logic board in the lab. The rest of it, which is coding based, you are perfectly fine to do at home. Finish your report at home, come to the lab, show your face, smile a bit, do a demonstration, and then submit and go home. Okay, very easy one. You don't need to waste time in the lab if you're not going to do it in the lab. Okay, so as long as you come to the lab, you do the demonstration, you submit, you can leave. Okay, for those labs that you do not need to use any of the lab facilities. Okay, tutorial, you have attendance and participation. Okay, so listen first. Don't say I never say. Okay, listen, important. Okay, this participation and attendance both got marks. Okay, participation means what? Participation means you will either be required to answer some question or you will be asked to come up to the board to answer some questions. Okay, so my requirement is as long as you participate 4 times in 11 weeks, you get full marks one. Which means what? Every other week you will participate finish. Alright? Okay, so in the tutorial, some questions will open up for discussion for volunteers to come. So you must be smart. The moment we say volunteer, the easy one, you quickly jump. You don't wait until the hard question, you don't know what to do. Alright? Okay, so have a good holiday. Enjoy yourself. Next week, Monday, tomorrow there's no class, correct? So I say next week, Monday, everything will start. So tutorial and lab. Please make sure you go for your registered class. Okay? If you cannot make it for whatever valid reason, you must inform us earlier. Okay? Thank you. Enjoy your holiday. See you all next week. Yes. Wait up. There is a limit to what, so we will, for us, because we only talk about the 32-bit representation, right? So some numbers cannot be represented. Why? It all depends on eventually what is the final exponent that you get. Because, for example, after I shift around, whether the practice and exponent, when I switch back, and I recover back. So the whole idea is what? When I get this number, I must be able to work backwards. Alright, so if I come across a number that this cannot be reversed back to this in a clear way, then that number cannot be calculated. You can try and see, you can try some numbers and see whether if I get this, will I get back this number. have for the overflow being later in processing you will learn that the error bits so when the error bits are set, it's not stored and something then you know the answer. For this 32 bit is the format. 64 bit is the
So for the negative, right, this one is negative, right, then you put the sign.
so basically because you are treating it as a positive number, right? So the maximum bit,
So for example, you straight away convert 6.5 to like
because the exponent is 8 bit.
like that, so it's 1.1.
Maximum,
Yeah, just now, if I'm not wrong, yeah, then after that you just straight away multiply to yeah, then add the amount of yeah. So you know 127 becomes plus 2, then this one becomes a fractional bit.
And the 127 came from like
For 127,
the one that is minus
127 plus yeah, then after that the result is just convert to yeah, then this plus this one is it's 101. Normally you know 101. Yeah,
depending on the class, some classes will have flexibility, so it is very close to instead of vector. Some classes is so what I would suggest is to go ahead to but you must stick to it lah. You need to register for one. Because it will be exponent minus the power, right, that you put in, right? So if you choose complement, then your limit should be the minus 128.7. That's the maximum number of bits you can shoot, correct? But you will not hit the limit because it's still a bit to bit regulation. So you will not hit the limit of the exponent. No, because you're still confined within the exponent. So you will not exceed the 8 bits. And the 8 bits gives you minus 120. Alright? But you will not shift so many bits anyway. Because the number you represent in bit should also be limited to 32 bits, correct? The whole number is 50. That means the maximum you can shift is 50 bits. So you will never exceed the exponent. We are given a form. How are you given a form for the talk to the teacher? one we normalize it, so we know that once we normalize, the 1 is constant. So we won't go wrong. Yes, correct. Yeah, because this was, if you, for example, let's say, okay, let's skip that. Let's say 0, 0, 1, 1. Okay? Let's say, I say 3. 3 you represent as 0, 1, 0. 0, 0, 1. Right? Now I say, give me minus 3. What will you do? You will say that, okay, to get minus 3, I will do this complement. Alright? Okay, so how is it just going? 1, 1, 0, 0, and then I add 1. Right? So it's a 1, 1, 0, 1. Alright? So now I tell you that, imagine you never see this now. I say 1, 1, 0, 1. Find out for me what is it. Let's go there. What will you do? So you say that this is the 1. So this is the 1. Alright? So what must I do? You find the original number. Because I got this answer because this came about because from some original x value this exponent, then I get this. Alright? So now I want to find this x value. What's the original number? Alright? So I need to work backward. So to work backward, I'm putting it again. So what must I do? So the first complement is 0, 0, 1, 0. So first complement is 0. So I invert that, then I add 1, I get 0, 0, 1, 1. Right?
So this is equal to 1 as well.
Yeah. So this is 3. But since the most negative is 1, yeah, so it's 1. Carry on after the most significant bit. So if the 4 bit means the 4th bit, after I finish, then the bit that comes out.
So this is.
The 4th bit. Yeah, 5th bit.
Okay, thank you.
Yes.
For this slide, right, the IEEE floating point presentation. For this number, why is it 101 then the rest are zeros? Why
Because-
isn't it 0000101?
Because you start off from the decimal point. You start from the decimal point onwards. So from decimal point is 101, correct?
Yeah.
But this whole thing is 23 bits.
Yeah.
So the rest will be padded with zeros.
So you pad behind and not in
Yes.
front.
Yeah, yeah.
Because the normal numbers you pad in front.
Yes, correct. So that is the format.
Okay. Then for this number, right, why do we add 1 to 7? Why not just put 2?
That is the formula.
But wouldn't it make more sense to just be 2 instead of just adding 1 to 7 for no reason?
No, because that is the formula because it's the 8-bit number.
Okay.
So for 8-bit number, your range is minus 128 to 127, alright? So that is why they use the 127 as the excess. So your 127 like become a new starting point.
Okay.
So it is like the excess representation. Okay, I mean they have a lot of thought and reasoning behind this lah. But this is the sort of format to follow.
I mean, why 1 to 7, why not 1 to 8?
Because okay, I need to go and look at all the video, but if you can go and find out. Basically, this is like it's like they consider a lot of options before they finally decide this is the best format. Alright, so there is a reasoning behind everything, but we don't need to go into that. For now we just focus on how to represent it using this format.
Okay. What if the number here is not 2 but it's like 1 to 8 and it overflows to 6?
Sorry.
What What if the number here is not 2, but it's 128 and it overflows this 8 bits?
No, the number will never overflow. That's why they choose this format. So for a 32-bit number, whatever you put in the exponent will always be enough to represent it.
But here you want to represent any number, right? So the number can be a Google, so it will be 2 to the power of the number above.
Correct. You see, but it's 127 plus this shift, correct?
Yes.
And how many bit can you possibly shift?
Could shift any number of bits because the number could be
But
very large.
correct. So for 32-bit, what they figured out is this will be enough for a 32-bit representation. If anything more than 32-bit, then you must use a 64-bit representation. Yeah.
So a 64-bit representation would mean that this 8 bits is doubled to 16.
Yes.
And similarly, there will still be an upper limit.
Correct. There will always be a limit. Correct. There has to be a limit.
So in this case, this number, you will say that it cannot represent a number higher than 2 to the power 128 plus ones in all of here.
Correct.
Okay. So for the 64-bit representation, is it still 1 to 7?
No. This is different. It's a different way of calculating. So they have different format depending on how you declare these variables, what data type you use. Alright. So the way in which you work backwards is different.
Like this.
So there is 10-bit representation. 11-bit representation.
Okay. And then the sign here says 1 is negative.
Zero.
So from understanding, this will always refer to the most significant bit. So if I have a number like a very large number, if I say 1, then 10,000 zeros, then 0.0005, you will lose that 0.005 because it can only represent the significant figures.
Yeah, so I mean, if the number is so big that it cannot be represented by this 32-bit, okay, and then you try to assign to it, then you will lose the actual value. The number that eventually gets stored could be something that is far different than what you originally intended.
But my number could, maybe it is within the range of a 32-bit number, but it has digits such that it will overflow these.
Correct. So if you try to do it, then you may see that the number may overflow. It may not fully be correctly represented.
Okay. So for 0.1, right, what do we consider it as in binary?
0.1.
Yeah.
Then you still need to do.
Because 0.1 you double, right? So it goes to 0.2, 0.4, 0.8, 1.6, you add a 1, 6 doubles to 0.2, and you can see a cycle repeat here.
So in cases where it repeats indefinitely, alright, then the representation will be using all the possible bits, but it will never be full precision.
So the full 32 bits as much as possible.
Yes, but it will never be fully representing the actual value.
So if this question were to come out in the exam, to write 0.1 in binary, you will write as many bits as they ask us. So if they ask us 32 bit, we'll write the full 32 bits, and then that's it. There will be an estimation.
That's why sometimes when you do a floating point, you will never be able to capture the exact number all the time. When you round off at the end, you will always do something.
Thank you. So point 1, you convert back is multiply by 2, correct? Multiply by 2 is the 1 from 0. Right, so the 1 means 0.5, correct? Yeah. So if there's a few like that. So like 0 will start from 1, 1, then also value like so whatever is the number, correct? Eventually, what is going to be a given value, correct? So for example, you can get. So if I say, so if I say
one is the multiplication, right? Times 2, then the answer will be 0, 0, 1,
So it's like 1 and
yeah.
1 is 1. Then the 125 is the 0, then the 125 will be 1. Oh.
Yes, yes.
So that's why if it does not overflow, how do you because we have decided.
Yeah, this is
But then how can we differentiate this one? So this one is also a minus 3. And in making the process, it differs between LS complemented and S complemented. One of the LS complemented exceeded and it has to add one.
the overflow comeback. Because in this case, this one we discussed, right?
Yeah.
But here, when we do one complement, when you have the 1 will bring down.
So this is not a
No, it doesn't matter overflow, but when I have the most significant bit carried out, this 1 will get add back into it.
this is minus. And this is
Here, the one that come out, I discussed.
I see.
In one's complement, the